and welcome to already the third week of Mastering Mathematics Calculus 1. At this point, it is time for a bit of a reality check. We have been considering functions from an abstract mathematical point of view. We will now need to face the fact that in actually applying functions, we are bound by our computing power and its cost. In particular, its cost in the sense of time. We can discuss the properties of a function like square root of x in the abstract. For instance, we know the derivative is 1 over 2 times the square root of x, and its maximal domain consists of all non-negative numbers. We can also provide some values of the function exactly, like square root of 36, which is 6, square root of 0.25, which is a half, or square root of 100, which is 10. However, can we also provide the value of this function at other points? Maybe ones that are quite close to the ones I just mentioned. Like, what is the square root of 101 in terms of a decimal expansion? Finding decimal expansions of function values is often important if we want to base decisions on our mathematical models, and if we want to do quick computations. We run into two major problems, however. First of all, like the case of square root of 101, sometimes the decimal expansion just keeps on going infinitely with no repeating pattern. Secondly, sometimes it is simply too hard or too time-consuming to find the correct decimals. In those cases, we employ approximations. Put simply, we provide instead of the actual function value, a decimal expression of a number we know to be very close to the actual value. For instance, we may approximate the square root of 101 by the square root of 100. We can then ask, is this approximation any good? Whether an approximation is good or not, depends first of all on the application. Some applications require a lot of precision, and in other cases it is okay to sacrifice precision to be able to compute more quickly. The way to quantify this precision is by considering the approximation error. The approximation error is simply the absolute value of the difference between the actual value of the function and the approximation. Sometimes it's more sensible to consider the error relative to the total value, since being off by 1 on a total of 1,000 is often less of a problem than on a total of 10. In those cases, we consider the so-called relative approximation error, obtained simply by dividing the approximation error by the function value. Of course, in general, we do not know the approximation error exactly, since if we did, we would be able to find the actual value of the function exactly. Often, however, we are able to find an upper bound for the approximation error, so we know how wrong we could possibly be. For instance, with the technique we will cover this week, we find that the approximation error for approximating the square root of 101 by 10, which is the square root of 100, is always smaller than 0.05. There are many better approximations to the square root of 101 than just using 10. We will cover the most important technique this week. We will see that the first improvement to the approximation 10 is the approximation 10.05, which has an approximation error of less than 0.000125. Already a lot better. Often, when we use approximation techniques, they will come with a restriction on the range of their applicability. This means that they will produce approximations with low approximation error only when we apply them for certain values. For instance, the approximation technique we will cover in the next video, and that was used above to approximate square root of 101 by 10.05 with an approximation error of at most 0.000125, would approximate the square root of 160 by 13 with an approximation error of at most 0.45. So we see that this technique does not really work to approximate the square root of 160. This is because the technique only works to approximate the square root of numbers close to 100. The further we go away from 100, the worse the approximation will be. Okay, let us end with an example. Here you see a still from the 1999 video game Quake 3. To compile this image and simulate physics in-game, many computations are necessary. In order to provide a smooth gaming experience, those computations also need to be done very quickly. One particular computation that arose a lot was to find the value of the function f of x equals 1 over the square root of x for various values of x. Programmers found a neat approximation technique based in part on some computer hacks, but also in part on the approximation of base 2 logarithm of 1 plus x by x. You can find comparison videos online of what the increase in computation speed by using this approximation did for the gaming experience. It did quite a lot. Here you see the graphs of the function f of x equals base 2 logarithm of 1 plus x and g of x equals x for x between 0 and 1. Note indeed that the graphs are quite close. Actually, the programmers of Quake 3 adjusted this approximation by adding a certain constant mu equal to 0.043 to obtain the following. Note that the approximation is now a bit worse at some points, but a bit better at more other points. So overall the approximation is a bit better. At least when x is between 0 and 1. As you can see, the approximation error gets a lot larger as x gets much higher than 1. Luckily, the computer hacks implemented meant that in a program x was always between 0 and 1, and so the approximation was always justified. Okay, make sure to practice the general concepts discussed in this video with the following exercises. After that, we'll start considering approximation techniques.